All right, hello everyone. I'm going to talk through the problems on the practice test. So this first one is a box or a block that is sliding down the ramp at a constant speed. So I'm going to draw on my ramp, and I'm going to add my force of gravity, which is just going to be straight down, my normal force, which is going to be perpendicular to the surface, and my force of friction, which is going to be parallel to the ramp and opposite of the motion. So because the block is sliding down, that means the force of friction is up the ramp. And because it is sliding, this is kinetic friction. Now, because it's moving at a constant speed, that means that my F net needs to be 0 because the acceleration is 0. And so I'm going to draw on my components so I can show that my forces are equivalent. So here's my FGY, here's my FGX. And my FGY is going to be equal to my Fn, and my force of friction is going to be equal to FGX. There's no push force. If you drew a push force going down the ramp, that is a phantom force. Nothing is pushing the block. Okay, I'm going to do this next one now. So we have a hanging mass that is smaller than the mass on the table. There is an additional force of tension, FTB, acting on the mass on the table, causing the system to accelerate in the direction of FTB. So what that means is that my system is going to be accelerating this way. And that means this hanging mass is going to be accelerating up. And that's because we tell you what direction it's going to accelerate. We are also told that friction is not negligible. So what that means is I need to show that there's a force of friction on the block on the table. So I'm going to start with my FBD for the block on the table. I'm going to draw an FTB. And I'm going to call it FTB because that's what the problem tells me to call it. I'm going to draw a force of gravity of the table mass, normal force of the table mass on the table mass. Then I'm going to draw on a force of tension because there's a string right here that it's connected to. But then I also was told that there has to be some sort of force of friction between the tables, so I'm going to call that force of friction kinetic. And it's still very clear that, and these are T's, not pluses, it's still very clear that FTB is bigger than the sum of FT and FFK on the left because, remember, the system is accelerating this way. And so what that means is FTB is going to be positive, FT is going to be negative, and so is the force of friction on T. Okay, now I'm going to draw my FBD for the hanging mass. So the hanging mass, there's a little force of gravity on the hanging mass, and then there's going to be a force of tension on the hanging mass that is going to be bigger than the force of gravity on the hanging mass because the hanging mass is accelerating up because the whole system is accelerating this way. And so then I can add that FT is going to be positive, FGH, so FG on the hanging mass is going to be negative. And then this FT is equal to this FT because it's the same string. Okay, now I can start to write F net equations, and I'm going to do that over here just for the sake of room. So I'm going to do the hanging mass first. And so I have FT is positive, FG on the hanging mass is negative, and then that's going to be equal to MH, because they tell me that's what I need to use, times acceleration of the system. Then for the block on the table, so the table mass, I'm going to have FTB, because that's what they tell me to call it. And then there's a negative FT, negative force of friction on the hanging mass. So I'm going to put a little H there just to remind, or on the table mass, sorry, not the hanging mass. So I'm going to put a little T there to remind me. And then that's going to be equal to mass of the table times acceleration. Now the table mass also is going to have Fg of the table mass and Fn on the table mass, and that's going to be equal to 0 because the net force is 0 for the vertical direction. Those two forces should be equal. Okay. Now down here, I'm trying to derive an equation for the acceleration of the hanging mass in terms of mh, mt, and ftb, and mu k. So I'm going to start with my table mass. So ftb minus ft minus this force of friction on the table mass. And I'm going to start to plug some stuff in. So I can break down the force of friction in terms of mu k times Fn on the hanging mass, because it is kinetic friction, so I can actually use that equation. And then I can, based on my equation up here, I know that Fn on the table mass is equal to Fg on the table mass, which would be equal to mass of the table mass times gravitational field strength. And so I can start to plug that in at least. Now, I'm not supposed to have Ft, I am supposed to have Ftb, but I'm not supposed to have this other Ft, but I can get rid of that other Ft by using my other mass. So by using my hanging mass, so now I'm going to flip-flop to my hanging mass, and I'm going to solve for Ft using that hanging mass equation. So I have this as my Fnet, and I'm going to solve for Ft. Can plug in mhg for the mass, the gravitational force acting on the hanging mass. And then I can plug that in for Ft into this equation. So then I get Ftb minus mhg plus mha, and then minus my force of friction, and then I need to get the a's together, but first I need to distribute this negative, so minus and from here it's really just a lot of algebra. So I'm going to add MHA to both sides. And then I can factor out H, or I mean A. And then I can get my expression for acceleration. Now, I'm going to show you another way to do it that's maybe a little bit easier, and that's the system method. So system method, I'm still going to use my two Fnet equations over here, but because I know that my net force on my system is going to be the sum of all the forces that are acting along the axis of acceleration, these are all the forces that are acting along the axis of acceleration. So I just did FTB minus FT minus force of friction, and then these are acting along the axis of acceleration as well, so FT minus FGH. And then remember, this is for my system, so that's mass of my system times acceleration. It's really important to label your masses. So now when I look at this, it simplifies to FTB. The forces of tension are going to cancel out. So then I have force of friction on the table mass minus force of gravity on the hanging mass. And then my mass of my system is going to be the sum of the masses. And now I can break down a lot of these forces just like I did. So I'm going to break down force of friction on the table just like I did over here. Except I'm just going to jump to the mu k times mtg. And then mass of the force of gravity on the hanging mass is mass of the hanging mass times g. And some of you may be noticing this, I get the same exact answer, except it's a little bit less math. Okay, now let's do this one. So I know that there's a 294 Newton object. Right away I see this FBD here, but even if I wasn't given one, I would be drawing one. 294 newtons is Fg because it sounds kind of like mass, but it's measured in newtons. And the scale reads 400. So the scale, remember, is the normal force. That's why you tell the doctor you're going to go normal force yourself. And so I draw my FBD, so Fn is much bigger than Fg. And what that tells me, and before I even answer a question, I am going to start with what's given to me. So I'm given that Fn is bigger than Fg, which means just by looking at my FBD, I can tell that Fnet is up. And because Fnet causes acceleration, A is also up. And then if that's true, well, if velocity is down and acceleration is up, then we would be slowing down because they're opposites. But if velocity is up and acceleration is up, that would mean speeding up. And so those become my two answer choices. So the elevator would be moving down and slowing down because that would mean velocity and acceleration are opposite. Or the elevator could be moving up and speeding up because the acceleration would be the same direction as the velocity. Okay, so now I'm going to draw my acceleration versus time graph for the elevator. And I know for this elevator, all I know is that it has a constant positive acceleration. And because the Fnet is the same for either option, for velocity going up or velocity being down, so either direction that it's moving, it still has a positive acceleration. And so my acceleration versus time graph would just look like a horizontal line in the positive quadrant because the acceleration is positive. And that could mean the velocity is up, so we're speeding up. But it also could mean that the velocity is negative, so we're slowing down. Either one, it could work. Okay. Now we have Mr. Fitz challenges his neighbor to a tug of war with tractors. A chain connects the tractors to one another. Mr. Fitz has a tiny Farmall Model A tractor while his neighbor has a big Case International tractor. The dude just destroys Mr. Fitz and both tractors accelerate to the left over the line in 3 seconds. Okay. How do the magnitudes of the forces that the tractors exert on each other compare? Right away, I look at this problem and I think, what is this question trying to test me on? And this question seems like it's trying to test me on Newton's third law. Because they're asking me a question about how the force on this little tractor exerting on the big tractor compares to the force on the big tractor exerted by the little tractor. So comparing the force on the tractor by the big tractor and on the little tractor by the big tractor. Or on the big tractor by the little tractor, and vice versa. And so automatically I am just searching for same force because I recognize that this is a Newton's third law problem. And I do that before I even really answer the questions, which is going to help me figure out what answer I should be looking for. Okay, so now Mr. Fitz is driving his tractor at a speed of 5 meters per second along a level road when a deer jumps out in front of him. He slams on his brakes and slides to a stop. The tractor doesn't stop instantly. What is causing the tractor to keep moving and to not stop right away? Well, the tractor has inertia because it has mass. And that means it has a resistance to accelerate. It takes time to accelerate and to change speed. So basically it just takes time to accelerate. They can't just stop automatically because they have mass. So they have inertia, so it takes a while for them to actually stop. All right, let's do this one. So we have to draw an FBD first. Even if we weren't asked to, we should. So we've got a force of gravity. We've got some sort of push force from the lawnmower. We've got a normal force, which I'm drawing really big, and we have a force of friction that is opposite the direction that it's moving. And it's moving to the left because we know that he's pushing it to the left. Now I need to break up my FP into components. So here's my X, here's my Y. My X component and my force of friction are going to be equal because it's a constant speed, and those are the only two forces acting. And then I know my theta is going to go right here. Okay, I'm going to write my F net equations. So F net X is going to be equal to the force of friction minus FPX. And again, those are equal to, they balance each other out because it's a constant speed. F net Y is going to be Fn minus Fpy minus Fg, and that'll also balance out to be 0 because it's not accelerating. And then I want to calculate what the magnitude of the normal force is, so I'm going to use my F net Y. And so Fn would be equal to Fpy plus Fg. And so I'm going to start to break those down. So Fpy was going to be the push force times, it looks like it's the opposite, so sine theta, plus the mass of the lawnmower times gravitational field strength. And then I'm going to start to plug stuff in based on the information that I'm given. And again, if you can't look at this vector triangle and figure out what the components are, that's not a big deal. Just draw yourself a triangle. So this is Fp, this is Fpx, this is FPY. So sine of theta is FPY over FP. Cosine of theta is FPX over FP. And so then I could solve those for FPX and FPY. But if I solve that over here, I would get FP, which is 120, times sine of 35, plus the mass times 9.8 would give me Fn, and I'm not sure what that is, but whatever it would be. And in newtons, you could plug that into a calculator and figure out what that is. Okay, so now instead of pushing but still at the same angle, now you're pulling. So what I'm going to do is I'm just going to copy this FBD. Right away, I draw an FBD. So think about that question on our Unit 1 summative, or our Unit 2 summative 1. Draw an FBD. Just because it doesn't ask you to doesn't mean you shouldn't. And so I know the force of friction is going to switch directions because now I'm pulling up, so I'm going to be pulling at this angle. And then I know my theta is going to be the same. So this will be where theta goes. This is FPY. This is FPX. And so that means force of friction would have to switch directions. Well, now I'm noticing that now I have two upward forces. Before I only had one upward force, which was just Fn. And now I have two upward forces, so that means Fn is going to get smaller because Fg is staying the same. And the Fnet still has to be 0. And so Fg is going to stay the same because same mass and gravitational field strength. Because neither of those are changing, Fg has to be the same. For Fn, now Fpy is up instead of down. Before, Fn had to balance Fg and Fpy to keep Fnet equals 0. But now, Fn and Fpy have to balance only Fg to keep Fnet 0. So Fn decreases. Okay, let's do this one. So Chili the cat is playing with a block on a rough incline. He paws it and it slides up the incline. So I'm going to draw in my surface. I'm going to have my force of gravity, my normal force. Okay, and it's going up the incline, the velocity, so that means the friction needs to go down the incline. Is there an upward push force? No. Okay, so now I need to break down my components. So I have FGY and FGX. FGX is parallel. Here's where my angle of the ramp goes. Fn and FGY are going to be equal. And then I'm going to start to write an FNet equation. So FNet Y is equal to Fn minus FGY. And because it's not accelerating perpendicularly to the ramp, the net force is 0. And then FNet X is going to be FGX, which is down the ramp, and FF, which is also down the ramp. So the force of friction and FGX are pointing the same direction. There is no opposing force. There's nothing up the ramp. And so they're both going the same direction. And then this is going to be mass times acceleration. Okay, so I'm trying to derive an equation for the acceleration of the block. So I'm going to start by using my FNet equation. So FGX in this case would be, I have FG, FGY, FGX, theta. So sine of theta would be FGX over FG, and cosine of theta adjacent, so FGY over FG. And so for FGX, it would be FG sine theta plus the force of friction, which is going to be, because it's kinetic, it's actually mu k times Fn. And then I need to use capital M for the mass because it tells me to use capital M for the mass. I should also actually just use mu because it tells me to use mu, not mu k, for the coefficient of friction. Theta is fine because that's the angle of the inclined plane. But right now I have an expression that has FG that's not allowed and Fn that's also not allowed. And so I need to get rid of FG and I need to get rid of Fn. Well, I can get rid of FG by saying mg. But I need to figure out how to get rid of Fn. So I'm going to start to look at other things that I have on my paper. And I do have Fn minus FGY. That's why it's so important to write down your FNet equations every single problem, because it puts stuff just in front of you for you to choose from. So FGY, I already wrote that out over here. Again, helpful because I already have written it out. So FG cosine theta is the same thing as FGY, which is the same thing as Fn. And so I can plug that in here. And then I can break down FG just like I did over here with mg. And again, I'm really just doing this because I'm trying to get it in terms of these allowed variables. And that's what tells me what I need to break down. Okay, then I'm going to get rid of the m's because m is in every single term, so I actually can cancel it. If it wasn't in like this middle term, if m wasn't there, I could not cancel m. And then I have an expression for acceleration. Let me double check it's actually in terms of things that are allowed. So g is okay because it's a physics constant. Sine theta is fine because theta is allowed. Mu is fine because mu is allowed. G is fine because it's a physics constant. Cosine theta is fine because it's a theta is allowed. And that is my expression. Okay, let's do this one now. So I have two teams are conducting an experiment similar to the one you did in Forces in Motion Lab, and then graphed their data on the same graph as seen to the right. So I have an acceleration versus FNet graph. So right away, I'm going to start with y equals mx plus b. On my y-axis is a. On my x-axis is FNet. And then I'm trying to figure out what goes in the slope, because these lines have different slopes. Well, I have an equation that relates A and FNet, and that's FNet is equal to mass times acceleration. But that doesn't really look like this equation, so I need to rearrange it so it looks like A equals something. So if I divide both sides by mass, I get F net over M. And so I need to make this equation look like this one. So if I plug in M, I would get A equals mass times F net, which is not the same thing as this. So it can't be mass. I would need 1 over mass. And that does work because that simplifies to F net over M, which is exactly what I have right here. And so that's what my slope is. My slope is 1 over mass. And so that means a bigger slope so a bigger slope, 1/2 is bigger than 1/4. A bigger slope would actually mean a smaller mass. So that means the dotted line group must have used, because they have a steeper slope, they must have used a smaller mass than the solid line group. And again, that's because the slope is 1 over mass, and we know that 1 over 2 is bigger than 1 over 4. But 4 kilograms is bigger than 2 kilograms. So a bigger mass actually results in a less steep slope. Okay, we've got another two-body problem. So I'm going to start to draw my FBDs. So we have, on the big 3M, we have F. It's frictionless, so there's no friction. We have an FG. We have an FN. And again, this is on the 3M. Those are going to be balanced. But I also have a force on the 3 by the 1M. And I also have a force on the 1 by the 3. Notice they're equal and opposite. They're opposite directions. And so they're equal and opposite. On by notation is flip-flopped. And so that is a Newton's third law pair. And then I have an Fn on the 1M and the Fg on the 1M. All right, write an equation for the net force on the small block in terms of the applied force F. Well, first I'm actually going to solve for the acceleration of the system. And so the net force on the system would be F minus F on 3 by 1 plus F on 1 by 3. And then mass of the system is going to be 3m plus m. And so what we end up with is F is equal to 4m times a. And so that means acceleration of the system is F divided by 4m. Then I can use that to write my equation for the net force on the little block. So the net force on the little block would be the little block times the acceleration. Well, I know the acceleration of the system. The mass cancels, and we get this as our answer for part B. Now the net force for the large block, we're going to do the same thing. So F net on the big block would be 3m times a, which is the same thing as 3m times the acceleration of the system. And we end up, the masses cancel, so you get 3/4 F. And that actually makes sense because the net force on the system is F, right? The net force on our system is F. And this has 3/4 of the mass of the system. And so it would make sense that if you have 3/4 of the mass of the system, you would need 3/4 of the F net for the system to accelerate at the same rate. Okay, now third law pairs. The only third law pair is F on 3m by 1m and F on m by 3m. Fn and Fg are not third law pairs, even though they are, in this case, equal and opposite. They're not third law pairs because they are both acting on the same object. So it would be Fn on m by the surface and Fn on m by the Earth. So they're not third law pairs because they're both acting on the m block. All right, so this is our experimental design. And I'm just going to talk through like how to think about an experimental design. When you read this problem, you can pull it at different constant accelerations, which are given to you. However, the speedometer on the car is broken, so you can't figure out what the speed is. You have spring scales. So we know a spring scale, that's what we use to measure force. That's a force measuring device. So I know that I can pull it at a constant speed as well as 5 different accelerations. So I want to figure out what the mass is of this crate. That's my question mark. I know the accelerations I can pull it at. So that probably means I'm going to want to figure out what the F net is. So I'm going to want to measure this. And it's good because I have a spring scale to measure. And I always like to start my experimental design with a graph. And so I want to be able to use my graph to figure out what my acceleration is, or figure out what my mass is. So I need to use my graph to make a graph that has something that means mass. So I'm probably going to do acceleration since that's given to me on my x-axis. That's like a variable that I can change. And then F net on my y-axis because that's what I want to measure when I'm accelerating it at these different speeds. Well, I have an equation that relates F net and acceleration. And so I'm graphing F net on my y-axis, and I'm graphing acceleration on my x-axis. That means my slope is going to be the mass. So this is now how I'm designing my experiment, is I want to know I want to be able to graph F net and A, and then my slope will be my mass. Okay. Well, the accelerations are given to me, so that's easy. My F net is a little bit more tricky. So I'm actually going to draw an FBD. So I know I have like this car that is pulling a crate. And so when the crate is moving at a constant speed, there must be a force that is opposing this like force of tension on the crate, and to make it go to constant speed since F net has to be 0. So there must be some sort of force of friction. So if I put this spring scale right in the middle here, I'll be able to measure the force of tension. And so when I pull it at a constant speed, that means that FF is equal to FT. So that's going to be an important piece of this data, is that this FT or this F pull that I'm measuring on the spring scale, they're equal when moving at a constant speed. Because the acceleration is 0, and so is F net. So that's going to be an important piece. Then to calculate F net for these other constant accelerations, what I'm going to have to do is I'm going to have to do Ft, whatever I'm measuring, minus the force of friction to calculate F net for each acceleration. So I'm kind of like reverse designing this experiment. So that's how I'm going to get F net to graph here, is by doing these two steps. The accelerations are just going to come from the given information on the car. And then basically I'll use the slope of line of best fit and that's equal to the mass of the crate. So now I need to actually write what I'm going to do. So this picture is going to be helpful. So the first thing I'll do is I'll pull, or actually first thing I need to do is I need to connect car to spring scale. And other side of spring scale to crate. Then I'm going to pull the crate at a constant speed. And it'll be important that I'm pulling horizontally so that the force that I'm measuring actually is equal to the force of friction. So it actually looks like this FBD. It doesn't look like this. And then I'll want to record that F pull from the spring scale. Then I'm going to want to pull the crate at the 5 different accelerations. Recording FT from spring scale each acceleration. And then kind of as a final step, I'm probably going to want to repeat steps 2 and 3, maybe like 5 times so that I can get some good data. And actually that'll probably be my first step here, is for the repeated, for the trials of each FT at the corresponding Excel, average the FTs recorded. So that'll be step 1. Then step 2 will be this section, so figuring out what force of friction is, and then being able to calculate F net for each acceleration. Then step 3 will be actually making this graph. And then step 4 will be finding that line of best fit, and that'll be equal to the mass of the crate. And that's how to do the practice test. I hope talking through this is helpful if anything you didn't understand on the key.